Okay, in last class, we talked about a very important concept, that is Kalman filtering. So the idea is you have a process that is Gaussian. You have a sensor measurement that is Gaussian. What you do is you combine these two Gaussians and find the resultant which coincides with the mean of the resultant Gaussian. We looked at the equation, update equation, Kalman gain. Then we talked about what happens for different values of Kalman gain, and then looked at the equation. Finally, what we did, we took an example and we followed the step-by-step approach of building the model, going through the iterations, and then finally converging to solution. One quick thing that in last class, I asked some of you to try the MATLAB code using Simulink. But if you look at Canvas, I have uploaded the solution for the MATLAB using Simulink. So that solution shows exactly how do you solve this voltmeter problem by creating a signal array and then passing that through the Kalman filter and finding the estimate and the covariance and so on. And I believe Thursday's lecture is already uploaded. If not, I will check. The next part is looking at the extension of Kalman filter, which is the extended Kalman filter. And once you understand the basic Kalman filter, the extended Kalman filter is sort of the nonlinear extension of the linear Kalman filter. So one thing that I want you to note, in the extended Kalman filter, the system dynamics equation. Earlier, our equation was x dot is equal to ax, but in extended Kalman filter, EKF, the dynamics is nonlinear. So the dynamics is nonlinear. So what do we do? At every step, we linearize. So this is what happens. So we linearize. And then what happens after linearization is we propagate. So as you see, the error covariance is propagated, and also the system dynamics equation is expanded as a series of time. Next thing is what happens in measurement. So this is the prediction step that uses the dynamics equation. In the measurement, assuming the measurement equation is also nonlinear. So we are assuming the measurement equation is nonlinear. So measurement equation is nonlinear. It's again linearized at every step. At every step, it is linearized. And then what we do is we find the values of the gain iteratively. So as you can see, you have a prior P that is multiplying with CI transpose, and that gives you LI, and then you find posterior, which is the update after you get a measurement update. And then you find the error covariance, which is posterior. So once again, there is the concept of prior and posterior. So prior and posterior. So in between prior and posterior, you have measurement update. And this is how the extended Kalman filter works. Now, if you look at, I just want to tell you what happens inside the MATLAB script. So if you use the EKF block for MATLAB, if you look at the EKF block for the MATLAB, what you need to do is you have to write these dynamical equations in a file, and that extended Kalman filter uses that dynamical equation that are written in file to linearize at every step. Now, please understand this linearization is numerical. This is not analytical linearization. So based on the numerical data, there will be linearization, and extended Kalman filter, that block uses this numerical linearization to propagate the system dynamics. And here is the EKF algorithm. And this EKF algorithm is very useful if you want to write your own code. But the good news is an optimal algorithm, optimal EKF algorithm is implemented in MATLAB, and that can be used. But you can see this is a step-by-step approach. And at this point, I would strongly recommend to watch MATLAB webinars. That gives you an understanding of the application of extended Kalman filter. Now, let's take a very simple example, which is a very common problem that we face. So attitude estimation using extended Kalman filter. Attitude means angle. So roll, we want to estimate, say, roll and pitch. So we want to estimate roll angle and pitch angle. Now, if you look at the dynamic equation, the equation that relates the derivative of roll angle with the roll rate and derivative of the pitch angle with pitch rate, these equations are given over here. So these are the equations. Now, one thing that you want to understand is these equations are not linear because of the presence of sine trigonometric functions. These equations are non-linear. And here, to make life complicated, there is this noise. So you have some noise in the pitch dynamics equation, which is theta dot, and you have some noise in the roll dynamics equation, that is phi dot. Now, let's understand the characteristics of this noise. This, whenever you see this type of symbol, that means it's a Gaussian noise with zero mean. So if you look at the characteristics of noise, this is how the noise is going to look like. Now, the accelerometers are used to measure the outputs. And what does accelerometer measure? Accelerometer, output of the accelerometer is nothing but, we looked at it, is the difference between the applied acceleration and the component of gravity. So the acceleration measures, or accelerometer measures specific force. Which is the difference between applied acceleration minus component of gravity. Now, here is the question that we are interested in finding out certain part rho and theta. So basically, this is phi d by dt of phi, and this is d by dt of theta. Phi is roll and pitch is theta. And these angles PQR are nothing but the body rates. So PQR are body rates. And I don't see rho anywhere. So G is the component of gravity, U dot, V dot, W dot are the accelerations in the front in the northeast down coordinate system, and you have UV, W, those are the velocities. And these equations come from the previous chapter, which is chapter, I think, 7. So look at the previous chapter. In the previous chapter, we talked about the sensor and measurements. So now what we are going to do is, here is the basic problem. We don't have a direct way to measure these. And the reason for that is because they are coupled with gravity. So how do we solve this problem? Now this problem is solved in an iterative fashion. So what we do is, we actually start with an approximation, then find solution, and then update, and then again iteratively we improve our solution. So the first and foremost, what we are going to assume, the accelerations of the plane in northeast down coordinate are 0. So if you have this plane, so you have north, east, and down. So accelerations are 0. We are going to assume the angle of attack, is equal to pitch, and the side slip is equal to 0. So as soon as you do that, you can see this equation simplifies. You get the component of airspeed. This is the airspeed, and this is alpha, and this is beta. So what you get is the component of airspeed. You can find out along northeast down direction, and that becomes your velocity in northeast down equation. Now, if you assume alpha is equal to theta and beta is equal to 0, this equation becomes super simple. What you do is, you substitute this equation in this previous complicated equation that you have. So you substitute this simplification in the previous equation, that gives you the equation which is over here. So this is an approximation of the original equation. So let's quickly recap. Compare this equation, I'm going to call this equation star, with the previous equation, which is equation O. So look at equation O and equation star. Equation star is an approximate value. Now what we do is, initially we assume x is equal to two states, phi and theta. U is equal to PQR transpose. We use the Gaussian noise distribution. And then what we do is, we write this expression for the actual velocity or actual state in terms of the state value and some noise value. And that gives me this nonlinear expression for the system dynamics and measurement. So please note, this is the nonlinear dynamics equation, and this is the nonlinear measurement equation. So quick recap, please look at what we have over here. This is our measurement, and this is our dynamics. So once we do that, we have these equations. We have an equation for f of x comma u. We have equation for h x comma u, and we have equation for gx, and that equation will be used for implementation in the extended Kalman filter. So these are the equations that are used for extended Kalman filter. How do we do that? For that, we find the Jacobians. So basically partial f by partial x and partial h by partial x. So this is nothing but a and this is nothing but c at each step. So these are the values that would be used as we go forward with the iteration. So now what we do is at every iteration, we compute these values, and just like the regular Kalman filter, we propagate. So what it does, it extended Kalman filter, you have nonlinear equations. These nonlinear equations are differentiated numerically at every time step to find the linearization, and this linearized system is propagated. And these are the results from actual and estimated. So as you can see, there's a solid line that is the true value, and estimate that is the dotted dashed value, and it's better. It's not perfect, but it's significantly better. So I would encourage you to look at the MATLAB tutorial on extended Kalman filter. So it's similar to the Kalman filter, but what you need to do is you need to write just like ODE solver, where we have the expressions as a separate function. You have to write down the dynamic equation as a separate function, and you have to write down the measurement equation as a separate function. The last part that we want to talk about is GPS smoothing. So here is the idea. So what you have is you have a GPS satellite. So you have this satellite and you have this receiver. And from this satellite, you have multiple satellites. You need minimum 4. And you are getting updates continuously. But these updates are not as fast as IMU or sensors. You get updates, say at 10 Hertz. So every second, you get 10 samples. Ten samples per second. Now, what we want to do is we want to fill in the gap between these 2 points. So we need to know what is going on over here. So what we do is first we assume the level flight, and we want to again we want to estimate the speed. So assuming the level flight, we actually write down the equation of position. So position in the north and east direction, if you look at the derivative, that is given as Vg cosine chi and Vg sine chi. And chi is, as you know, this is the path angle. And then what you do is, if you look at the derivative of the ground speed is always Vg. Ground speed is equal to air speed plus wind. So the ground speed is the air speed plus wind speed. You find the derivative, and at that instant, you assume the wind and the air speed are constant, and then you have the relationship that is given in terms of chi. So as you can see, you get the equation for chi dot, and you assume the rate of change. Actually, you assume that the rate of change of wind speed is constant. So you have an equation for the heading rate, and with that, you actually define your function. 10 samples per second means you are getting data at 0.1 seconds. Ten samples per second which means one sample is equal to 1 by 10 second, which is 0.1 second. So what you do is you define your state vector as the north, east position, ground speed, chi, wind vector, and the heading angle. And then you have your U as VA, QR, uh, the roll, and the pitch angle. And your function, so for GPS, if you think about it, GPS calculation is first and foremost is extensive. You need to get the timing right. And on top of it, the receiver, the computations you need to find the GPS solution are intense. So in other words, it's a combination of hardware limitations and again the wireless receiver limitations. Sometimes the receiver cannot get or acquire the signal, and sometimes the hardware that is needed to compute the solution is not available. Now the next part is, how do we find out? So how do we find out the Jacobian? So once again, this is how we find the Jacobian. So this is the Jacobian, and this Jacobian is used in every iteration to find out the answer. So what we are going to do is, this equation for Jacobian will be used in the filtering algorithm. And what we do is, with GPS, if you want to estimate the wind velocity, then we use the wind triangle relationship. And again, one thing that you need to keep in mind is the GPS signals, the north and east direction, ground speed, all these states are coupled. So you have the wind triangle that is combining the ground speed and air speed. So if you assume the value of gamma is equal to 0, which is the flight path angle is equal to 0, then you can actually write the relationship between the heading, wind velocity in the north direction, and chi as shown over here. This comes from the wind triangle. And now on top of it, you have the GPS update. So just like GPS update, you may define something called as the pseudo measurement. And these pseudo measurements give you the relationship, again, that is in between these two. So what do I mean by pseudo relationship? If you look at the expression that is shown for the pseudo measurement, is nothing but the residual between the left and right. So if you look at left and right side, this is the difference. Y wind triangle north and Y wind triangle east is nothing but the difference between these two. That's why it is called as the pseudo. And then what you do is, you land up with this expression that is the measurement equation. So this is the measurement equation. And you can use the extended Kalman filter to find out the smoothing of data. So you can see, if you look at the estimates and the actual GPS values, you will notice that you will get the good interpolation result in between the update rates. Now, some of you may ask me, it looks complicated, how it can be implemented. The good news here is, if you look at the MATLAB block, there is a GPS block that can be used for MATLAB. So if you want to get a GPS measurement, what you need to do is, you need to provide with the latitude, longitude, sort of geodesy coordinates, and then you can actually find out the values in the Earth center, Earth fixed coordinate frame. that block can be coupled with extended Kalman filter or Kalman filter along with IMU block that will give you a navigation simulation. And as a matter of fact, if you look at the next project, that in that project, we are asking you to do something similar. So in the next project, we are asking you to come up with the GPS model, and we are asking you to come up with a sensor model, and then find out the statistical parameters for the sensor and the GPS. So there is something that is commonly used, which is called as the measurement gating. So the measurement gating means if you have a measurement, say for an example, if you have this, these are the updates, and all of a sudden you get updates that are outside the potential solution. So if you have updates or if you have outliers that are significantly outside uh, the domain of a measurement, then your solution is going to be super duper inaccurate. So for that, what you want to do is you can estimate this, or you can gate, or you can neglect this measurement, and you can neglect this measurement based on the extended Kalman filter and Kalman filter implementation. So what you do is you define something called as the innovation sequence. Innovation sequence is nothing but the difference between the measurement and the update. And then what you do is you find the covariance of this innovation update. You find the covariance of innovation update, and then you implement this algorithm. So what you do is you try to find out the likelihood of that measurement being part of the sequence of measurement. So here is the basic idea. So we are assuming our measurement to follow some sort of a Gaussian path. So what we are going to do is, as soon as we get a new measurement, we will see if that measurement is actually fitting into what we have over here. Is it following that Gaussian trend? And if that measurement is following the Gaussian trend, we consider that to be a valid measurement. If that measurement is not following the Gaussian trend, we say that that measurement is not the true measurement. And that could happen because of either multipass or sensor glitch, or sometimes there is a quantization error. Sometimes the update rate or computation get mismatched. There is some floating point error. So what you do is you, every time you get a measurement, you find the likelihood that it's computed from a chi-square distribution. And if you find that chi-square is the measurement is part of chi-square distribution, then you use that measurement for updating. Otherwise, you just drop that measurement and go to the next sequence. And how do you tune your extended Kalman filter? Extended Kalman filter tuning, again, the easiest way to do that is use MATLAB for simulation, but you can do extended Kalman filter in steps, and actually you can use that to estimate attitude. You can use that to smooth GPS measurement. You can use these two independent components and compare their performance. And then finally, you can see if you combine those together, how does the performance change? Again, extended Kalman filter and uncentered Kalman filter, there is a lot of information that is available on MATLAB website. Again, there are lots of good webinars. So I would encourage you strongly to first master the Kalman filter. And once you master the Kalman filter, understand extended Kalman filter is linearization of the equations and using the Kalman filter. With that, we wrap chapter 8. And at this point, I want to ask you if there are any questions. If there are no questions, I will go on to chapter 9. I saw one question with project 9. So project 9 is completely sort of self-study. So you will have to do those webinars on your own and complete those exercises. And once again, that I have extended the deadline for project 8 and project 9. Okay. Any questions at this point? So what are the most important points that I want you to take from this chapter? So first and foremost, I want you to understand the heart equation for Kalman filter. So if someone asks you what is a Kalman filter, you should be able to tell them what is the Kalman filter. If someone talks to you about the sensor model and the GPS model, you should be able to tell them what are the different types of errors and how you can find out the correct measurement. And then finally, when we look at the simulation, we should be able to implement the state estimation updates. So we should be able to estimate states from the measurement that may not be accurate and the system model that may not be accurate. So all this is needed in chapter 8. If you look at the project for chapter 8, I would encourage you to take a look at it. It's a very simple project. You have a GPS.m, you have measurement.m. Those files you will use to construct the mathematical model for sensors and the GPS. And with that, I'm going to start next important chapter, which is chapter 9. Okay, now since you have mastered in chapter 5 linear design models, now what we want to do is we want to extend what we talked about in chapter 5 and study briefly nonlinear design models. And if you recollect in chapter 5, what we did, everything start with the equations on the Genesis block. Remember those 12 state equations, those form the basis for all this analysis. What we did, we linearized those equations and we created or constructed transfer functions, and we used those transfer functions for linear analysis. That linear analysis was valid in a very small region where the linearization is valid. So as soon as you cross that domain, then those assumptions will no longer be valid and you are not gonna get good solutions. So for that, what you need to do is you need to linearize at every step, just like extended Kalman filter. Or what you can do is you can try to go with a nonlinear design model. So in this chapter, we will talk about what is nonlinear design process, how to design the nonlinear models, how do we use those nonlinear design models to construct reduced order models that capture the dynamics of the original system. Because if you look at the nonlinear design models, they are going to be super complicated. So it may not be possible realistically to simulate nonlinear dynamical systems that are large dimensional. So what we do is we try to construct a small subset of equations that captures the essence of the dynamics, and we use those to study further. So in this architecture, we are looking at designing or controlling the unmanned vehicle, but our equations are now nonlinear. So first and foremost, let's quickly recap the process of simplification. So whenever we are trying to design an autopilot, we are looking at system that can be implemented in real time, because autopilots sometimes you have a nonlinear equation. If you use MATLAB on a CPU, on a computer, you may get reasonably accurate solution very quickly. But if you look at implementing that on a real-time operating system or real-time hardware, the solution may be complex and you will be limited by the hardware limitation, power consumption, and update rates. So the idea is we want to capture the essential behavior, and it may not be super duper accurate, but we are okay with slightly less accuracy as long as that model can run fast in a reasonable amount of time. So the objective here is that we want to derive, a reduced order model that is of less complexity than the original model, but better than the linear model. And there are two ways these models are designed. So there are two types of model that are possible. One is called the kinematic model, and the second one is called the dynamic model. In the kinematic model, you don't consider aerodynamic forces. So no forces. In dynamic model, you consider the forces and you apply Newton's law at every point to find the dynamic equilibrium and magnitude. So let's look at what we did so far. So first and foremost, if you look at your last assignment, at the end of working out the problem, you had relationship between the commanded airspeed. This is commanded, C stands for commanded, and VA is here, this is actual. And from the dynamics equation, you came up with the state space transfer function model. So this is the dynamics equation. This is how the VA is going to change. This is how the phi is going to change. This is how the altitude is going to change. This is how the course angle is going to change. And then you came up with the heading model, and then you came up with a flight path model. But this is something that I want to talk about. This is called as load factor. Load factor is the ratio of lift divided by weight. And many a times in aerodynamics literature, load factor is used to define the dynamics of the aircraft. So now let's look at the autopilot models in time domain. So these are all the transfer functions. So as you can see, these two are first order transfer function. Why these are first order transfer function? Because only one S. This transfer function is a second order transfer function. Why the second order? Because S square. This is also second order transfer function. So if you express these transfer function, this is all in frequency domain. In time domain, these are the same expressions in time domain. So as you can see, the first two expressions, these first two expressions, I'm going to call this star, are expressed here. These two expressions, I'm going to call this double star, is expressed over here. This expression is I'm going to call triple star. This is expressed over here. And the last expressions, I'm going to call this star and O, is expressed over here. And these equations are not new. These are the exact same equations that you constructed Simulink blocks for and then implemented in your last assignment. Now, what I'm going to do here is I'm going to express the kinematic model. And if you look at the kinematic model, this is the aircraft, this is the ground speed. VG is the ground speed. Ground speed has course angle. This is the course angle. This is the flight path angle. So in inertial frame, I can find out the component of VG, which is the ground speed. In inertial frame, I can find out the component of ground speed. And then that speed in the inertial coordinate is nothing but the velocity in the north direction, velocity in east direction, and the velocity in down direction, which is nothing but rate of change of altitude. So this is the velocity in north direction, velocity in east direction, and velocity in down direction. Now I can use the wind triangle and relate Vg is equal to Va plus Vw. The ground speed is equal to air speed plus wind triangle or wind speed. And this is the expression that we have looked and studied in detail in past. So this is the expression. Now what we are going to do is we are going to make some approximations. And first and foremost, I'm going to assume gamma A is equal to 0 and WD is equal to 0. So I don't have any values of gamma. My flight path angle is 0. So as soon as I do that, you have an expression which resembles the expression for car. So that's why this is called as Dubian's car model, which means you don't have any elevation or flight path angle. You just have the so what this means is if you look at H dot becomes 0. So as if its aircraft is behaving like a car, it's not pitching upwards, it's going in a level flight. So with this expression, what we do is we try to relate this with the coordinated turn concept that we talked about in chapter 2. So coordinated turn is aircraft is turning and banking. It is turning without slip. So basically aircraft is turning and rolling at the same time. And what we do is we have derived this equation for chi dot. And if you don't remember this equation, I would recommend that you quickly look at the discussions we had in chapter 2 and look at the coordinated turn expression. In the coordinated turn, the aircraft is actually turning, it's yawing and banking. Now what we do is, since we are assuming a constant altitude flight, which means H dot is equal to 0, and there is no down component of wind, the expressions that we derived can be significantly simplified as these two expressions. And these expressions are similar to the expressions 2.9. Only thing is those complicated equations are solved for us, and this comes out as the solution. But this expression, which is called as the yaw rate, we already derived. So yaw rate, this expression for yaw rate, that how quickly the aircraft is yawing. So as you can see, this yaw rate, the important point that I want you to notice, for a constant yaw rate, you have some value of roll angle. That's why when the aircraft is turning, you will notice that aircraft banks. So it turns like this. aircraft does not turn like car. So if you look at the car, this is car will turn like this, but the aircraft will actually bank. There will be certain amount of roll that will cause the aircraft to go do a coordinated turn. We also looked at something called as the accelerated climb, which means when the aircraft is climbing. And when the aircraft is climbing, we looked at the summation of forces. We applied Newton's law and we found out the value for gamma dot. So this expression comes from chapter 2. Now, at this point, when we looked at chapter 2, we did not study something called as the lift factor or load factor. So now let's introduce the load factor. Load factor is the lift, which means the upward force, and the weight, which is the downward force. So if the upward force and the downward force, they are the same, that means the aircraft is in level flight, which means the lift factor is equal to 1. If the lift factor is greater than 1, that means the aircraft is climbing. If the lift factor is less than 1, that means the aircraft is losing altitude. So if the aircraft is in horizontal flight, then the lift factor is equal to 1. And these equations can be utilized to find out the guidance model. And if you look at the literature, there are lots and lots of guidance models on the aircraft guidance, kinematic guidance. And depending upon the fidelity, depending upon the accuracy you need, you can choose different models. And depending upon the application, for an example, if you have an aircraft that is slowly moving, then you have a different guidance model. If you have a fighter aircraft, then the guidance model for the fighter aircraft is going to be different. The guidance model for the missile will be totally different than the aircraft. So we choose, what we are going to do is, we are going to start with a very simple guidance model. Now, once again, what is this guidance model? Guidance model is nothing but the dynamical equation, the differential equation that relates some of the important states of the aircraft to the dynamics. So as you can see, the states that we have chosen, they are important for our first guidance model, are the velocity in the north direction, velocity in the east direction, the rate of change of chi, which is the course angle, rate of change of altitude, and rate of change of airspeed. And these values are the commanded values that are actually substituted. And then you can find out the value of heading by integrating these equations. And please understand, these equations, we are ignoring noise and other parameters, but these equations can be numerically integrated and the value of psi or the heading can be found out. A second kinematic guidance model is used when the autopilot is designed to command heading instead of course. So what you're interested in, control of psi, not chi. So in that particular case, your guidance model is different. And once again, please try to understand this guidance model does not involve any external forces. It's purely, this guidance model is generated based on purely sensor inputs and kinematic data. So these are the differential equations that are used to find out the propagation of velocities and roll rate, the evolution of heading angle, altitude, and airspeed. This is a slight variation of the previous model. In this model, what you do is you make some changes to the roll angle and use the coordinated turn model. So one thing I want to tell you that these guidance model, they are applicable for particular flight envelope. So for an example, when the aircraft is in level flight, when aircraft is flying in a straight level direction, maybe the first model that we used is sufficient because the aircraft is in level flight. It's not changing in roll, it's not changing in pitch. Now, if you have aircraft that is sort of doing a coordinated turn, then what you do is when the sensors indicate that the aircraft is turning, then the autopilot algorithm switches from model 1 to model 2A. So what happens is these guidance models are valid for different flight regions, and you have sensors or you have some sort of logic that tells you out of these guidance models which guidance model is to be used. For an example, if you use these equations, if you use this model 1A, when the aircraft is turning, your values are going to be super inaccurate because this is not the right model to choose when the aircraft is turning. So what you do is when the aircraft is turning, you use this model. And how do you know if the aircraft is turning? The aircraft is performing coordinated turn is you can look at the simultaneous values of roll angle. You can look at the values of heading. You can look at the GPS positions and then make an observation that, hey, the aircraft is turning. As soon as you have that switch, you shift on to this guidance model to propagate or to compute the solution in that flight region. Again, these guidance model are used to find out the instantaneous values. These are nothing but differential equations. These differential equations are numerically integrated to find out the next value. And those values get updated from the sensor measurement. And you can definitely implement a Kalman filter or extended Kalman filter if need be to improve those estimates. So if you look at the guidance model, this comes from a very simple approximation wherein what you have is you estimate the values of chi and Vg from the wind triangle. But what you'll do is you'll integrate these equations, you'll propagate these equations through numerical integration. And then find out the next model, next response or next step. So next model is if you want to look at the flight path angle. Now, what do I mean by flight path angle? When the aircraft is climbing up. When the aircraft is climbing up, not only the roll angle is changing, the heading is changing, but the inclination of the aircraft is changing. So at that time, what you want to do is these equations replace the earlier set of equations, and these equations are propagated or used or found the numerically propagated to find out the next step. The next guidance model is using something called as the load factor. Now, one thing that you want to understand that in this, it's a kinematic model. And if you think about the load factor, it's sort of a dynamic quantity because it is considering the forces, but load factor is nothing but a ratio. So that's why this ratio is sort of propagated throughout the equations. So now here, as you can see that you are appending this equation for load factor, and that equation gets propagated. And finally, you find out chi, Vg, and gamma from the wind triangle. So these equations are kinematic guidance models, which means what you do is you are just interested in the quantities like velocities, accelerations, angles. There are no forces and no moments, but we can introduce forces and moments in the model, and now it becomes the dynamic guidance model. So for an example, if you want to incorporate the ground speed course dynamics, that can be expressed as forces: thrust force divided by mass, drag force divided by mass, and the component of gravity. So if you look at this aircraft and if you draw free body diagram, then you will see that force is equal to mass times acceleration. Acceleration is Vg dot, and forces are the sum of drag force, lift force, uh, thrust force, uh, and component of gravity. So those equations yield this. And when you use those equations, you can get a very nice equation for chi dot, which is the rate of change of course angle that is given in terms of lift force. So now you have an expression that gives you the rate of change of ground speed, and you have an equation that gives you rate of change of course angle. With this information, you have this dynamic guidance model. And this dynamic guidance model is quite powerful. So what you have now is not only you have the kinematic model, but this kinematic model, as you can see, gets updated with the equation for dynamics. And once you have these equations, you can find out the values of VA and psi. This is just one of the dynamics model, and this is a very simple dynamics model. As you look at more advanced aircrafts, more complicated aircrafts, the aircrafts that operate at different flight regimes, your dynamics guidance model are going to be complicated. And then following the basic assumption that we have no wind or wind velocity is comparatively small, your dynamic guidance model gets updated, and wherein what you do is you substitute the input thrust, lift coefficient, and bank angle or the roll angle, and your equation, the dynamic equation, can be updated. Now, let me clarify. Some of you may ask me, what is the fundamental purpose of this kinematic model and dynamic model? So think about an autopilot. What you want to do is you want autopilot to somewhat compute the next step so that we know where the aircraft needs to go. So these equations are programmed on an embedded system or a hardware platform, maybe written in C or C++, wherein the values of Pn at every time they are computed. Value of H at every time is computed. And those give you some sort of guidance, like this is the path the aircraft needs to take, or these are the next values of the states that the aircraft needs to follow. And that depends completely on the flight regime that the aircraft is pursuing. So this chapter 9 that talks about deriving these complicated models. These are nonlinear models, but one thing I want to emphasize that these are not the complete 12-state nonlinear models. We are looking at a very small set of equations. That's why it's called the reduced order equation. And we are using those reduced order equations to propagate inside an embedded system platform. And this is something that was done when the autopilot hardware was very limited. But with advanced autopilot hardwares, with advanced computational power, many a times what you can do is you can run the full nonlinear system on an embedded system platform. The problem that used to be was if you were to have a full-blown model running on a simple hardware, embedded system hardware like Arduino, or if you look at a microcontroller, then either the microcontroller will not give you the answer, or it will take a lot of time, or the power consumption exceeds. So, but with the recent microcontrollers, microprocessors, complicated guidance model all the way up to 12-state guidance model can be implemented in Autopilot. But this is how you can start and you can actually implement a simple guidance model for the Autopilot. Okay, with this, we finish this chapter. And if you have any questions, I would be happy to answer. If there are no questions, I'm gonna stop here today. And next class, I would spend some time on how to work out, or I will give you some hints on the project. And then we will talk about the next chapter. Or what I would do is I will demonstrate some MATLAB assignments using this reduced order models. So I'm going to stop recording. If you have any questions, I would be happy to answer.